Now we want to talk a little bit about implicit differentiation, and it's actually more of an alternative to implicit differentiation than actually implicitly differentiating. So basically, we can kind of take this idea of partial derivatives and use it to replace some of the stuff that we did with implicit differentiation. Because you might have your own opinion on it, but implicit differentiation is often just kind of seen as like it's a little bit messier than regular differentiation, right? Because you have like these y primes in there and you have to do some algebra to solve for it. And that can be kind of hard sometimes if you can't get the y primes by themselves. So it's good to have an alternative method, which is a bit easier. So just as a reminder, right? So with implicit differentiation, if we had the curve x squared plus y squared equals 1, for example, so the unit circle, then the idea here is that y is a function of x, okay, but it's defined implicitly rather than explicitly, right? Meaning that it's not by itself, basically, right? So we're doing something to the y's too, we're squaring them. So if we wanted to find dy dx, what we would do is we would differentiate both sides, employing implicit differentiation if we needed to. So we're differentiating with respect to x. So the derivative of x squared with respect to x is just 2x. The derivative of y squared with respect to x is 2y times dy dx. Okay, and then the derivative of the constant is still 0. So ultimately, we would solve for dy dx here, and we would get that it's equal to negative x over y. Okay. So this, what we're going to look at here is an alternative using partial derivatives. Okay. So what we want to do is we want to so I guess I'll call it move everything to one side. Okay. So in the x squared plus y squared equals 1 case, this would imply that we would have x squared plus y squared minus 1 equals 0. Okay. Call this equation z equals f of xy. Okay. So in this case, f of xy then is equal to x squared plus y squared minus 1. Okay. Meaning that if f of xy equals 0, then we have the original equation. Okay. Then dy dx is given by the negative partial f partial x divided by partial f partial y. Okay. You'll often see these typed kind of like horizontally or maybe slanted, just kind of just to save space, I guess. So that's why I'm kind of writing it like this, because that's usually how it's typed. Okay. But anyway, so this gives us a new equation, which is much more straightforward for finding this derivative. So now we take the partial, so like let's just do it right here, right? So then dy dx is equal to negative of partial f partial x, so that's just 2x, over partial f partial y, so that's just 2y, so equals negative x over y. Okay. So in general, this is significantly easier because it kind of takes out the algebra aspect of implicit differentiation. So just to look at another example here. Okay. So if we have x squared plus 3y squared plus 4y equals 4. Okay, so this describes an ellipse. then what we do is we take the equation with everything on one side. So we subtract 4 from both sides, and we set that equal to f of x, y. So we call this a function of f of x and y. Then dy dx will be equal to the negative partial f of x with respect to x, so 2x, and that's it, over the partial with respect to y, so 6y plus 4. We can cancel a 2 out of everything if we want to. So we get negative x over 3y plus 2. Okay. So the old way of implicit differentiation works just fine, but this is just kind of an easier and quicker way to carry that out.